Hi, welcome to Lab 5, Faraday Braking. In this lab, the purpose was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and then model the magnet and tube interaction computationally. We then had to compare the computational predictions with the observed data. The fundamentals at play here are Faraday's law, Ohm's law, the Biot-Savart law, magnetic forces and those associated with loops, varying magnetic flux, and Newton's second and third law. The equations associated with these are seen off to the right. As we get into these, the model I used came from the starter code, and I added some code of my own to create a glow script simulation of a falling dipole, magnetic dipole through an aluminum tube. The preview of the results is that the experimental fall time was 1.14 seconds, while the simulated fall time was 1.164 seconds. We had to make some assumptions here, and the first of which was that there was negligible air resistance, and the second of which was that there are only two forces acting on the falling magnet, the first being gravity and the second being the magnetic force. The initial conditions here was that the initial downwards velocity of the magnet was 0, and the height relative to the top of the aluminum foil roll when released was also 0. The system was the aluminum tube and the magnet, while the surroundings was everything else. As we get into the actual experiment, the materials that we needed was one center roll of aluminum foil and one bar magnet identical to the one used in Lab 3. As we get into the actual procedure, first we did take a look at the magnetometer app that we used in Lab 3. We used that again to determine the north pole of the magnet, and we placed an X on the north pole with a dry erase marker. A camera was then set up to record the following drops of the magnet through the aluminum foil tube, and then we actually, as the camera was rolling, we dropped the magnet through the foil tube 5 times. Then to find the time for each fall, we then ran it through a video editing software to ensure accuracy, looking at the timestamps of the magnet going in and coming out. As for the dimensions of the actual aluminum foil roll, the length was 0.35 meters, the width was 0.00256 meters, the radius was 0.0194 meters, while the mu of the actual magnet was 4.21 ampere meter squared, and the mass of the magnet was 0.025 kilograms. You can see on the right the actual different trials for the data, where trial 1 is 1.5 seconds, and as we go through, we can see the average fall time, and as we get our experimental fall time for the magnet, was 1.14 seconds. Why can't we use a ferrous tube, for example, a steel pipe? Well, we have to think about what would be in a ferrous tube, something that has magnetic properties such as iron, and there could be induced magnetic fields that would cause data corruption, which would skew data and make the lab inaccurate. So what actually happens to the magnet, and how does this compare to a magnet falling in free space without a tube? Well, obviously the magnet falls at a speed much lower than it does outside the tube, and I actually made a small observation where, looking from the top, it seems as though the magnet travels at a constant speed for much of the distance. As we get into the code, we can see in the top left, I initialized some of my variables and put in some of the measurements that we got from the actual lab itself. And then as we go through this, I do more of the same. As we go here, I define the actual magnetic field from the dipole, and then the actual magnetic flux from the dipole as it changes its position. As we go through this, I do more of the same, where we calculate some of the magnetic forces for each of the different rings of the simulated tube. As we look at this, we can see the results of the computational model here in the top left. You can see the blue and red induced currents, which we will talk about in a sec. The plot in the middle of the velocity versus time, and we'll talk about that also. And then you can see the time in tube simulated was exactly 1.164 seconds. So which color corresponds to the clockwise current, which counterclockwise, and how do you know? Well, we know that the red is the counterclockwise current, while the blue is the clockwise current, and this is because of Lenz's law. Because nature of force change, it does not want the magnet to fall through the tube, so it induces a B field with an induced current to try to push it back up. What happens to the dynamics of the system when you flip the magnet around? Nothing. I actually tried this experimentally in Lab 2, where we put the north pole in the opposite direction, and nothing changed. How does the total time in tube of your real-world system compare to that of a computational system, and how might the computational system be made more accurate? Just as is the case with any computational model, if we compute it with larger sample size, that being smaller rings, we can get a more accurate simulation. But that would always be the case, even though I only have 2.06% error. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, on either end, because that means that the forces are unbalanced, which would mean that the gravitational force is more powerful than the magnetic force there, pushing up. But in the middle, where it is flat, there's no acceleration, so the forces are equal, where the gravitational force equals the magnetic force. As we take a look at the discussion, for the sources of error, it could be a timing error, or I released it not exactly at the top of the aluminum foil tube, so the initial velocity was not 0, or it could be a mu error from Lab 3. What if the resistivity of the conductor was reduced as close as possible to 0, and how would the dynamics of the falling magnet change? If the resistivity was went down to zero, the induced current would go up, which would mean that the magnet would fall slower through the tube. What if holes or slots were cut in the tube? How this would affect the ring currents in your model? There would not be able to be full ring currents induced because there would not be a complete circuit, so the magnet would fall faster as there could not be complete circuits through. So what if Faraday's law applies to changes? Some conclusions that we had were that Faraday's law applies to changes in magnetic flux that come from moving magnetic dipoles, while Ohm's law helps understanding of resistance and its connection to current.